Morning, everybody. Our second lesson in the probability unit is experimental and theoretical probability. And again, the best way to attack some of these concepts is just to get right into it with an example. And that's what I'm going to do. So we're going to do sort of a pretend simulation, and obviously this would work better if I had your participation in the classroom, but we're going to do the best that we can here over the camera. A multiple choice test is made up of 10 questions, and there are 5 choices for each question, A, B, C, or D. So what you're envisioning is question 1, A, B, C, D, E. You choose question 1, A, B, C, D, E. You choose that type of test, okay? You are absolutely not prepared for the quiz, so you're forced to guess at every answer. What is the probability that you're going to pass the quiz if these are the actual answers? Okay, those are the solutions right there. Now, we need to simulate this. And normally what I do is I use the random integer function on the graphing calculator, and it will make pretend guesses for me, okay? The number 1 would represent an A, the number 2, a B, 3, C, 4, D, and 5E. But because I don't have a graphing calculator here at home, what I'm going to do is we're going to do 2 trials, okay? And basically a trial is like me writing a pretend quiz and guessing. So trial 1, trial 2, trial 3, and trial 4. Now, I am going to cover up the answers so that you guys don't think that I'm cheating. And after each trial, or each quiz, each pretend quiz that I'm going to take, I'm going to give myself a mark out of 10. Okay? Remember, my choices are A, B, C, D, or E on each question. All right, well, you know what? I'm going to guess A on question 1, C on question 2, D on question B, E on question 4, B on question 5, B on question 6, D on 7, C on 8, E, and E. Okay, so there's my pretend quiz, completely guessed at every single answer because I'm completely not prepared. I'm going to uncover. Remember, the answer key is right here. Yay! I got A right. I didn't get B. I didn't get the next one. I did. I didn't. I didn't. I didn't. I didn't. I didn't. And I did. So if this was my pretend quiz, I'd get a mark of 3 out of 10. Okay, let's do it again. I'll cover up everything. That way I'm not kind of cheating. Okay, so I'm going to give myself a B, a C, a D, an E, an A, an A, a C, a C, a B, and a D. Again, that's my second pretend quiz. I'm going to mark it. Nope. 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 Yep. Nope. Yep. Nope. 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 Geez, I did worse on this one. I got a 2 out of 10. Okay. Let's do it again. I'm going to give myself a C, an A, a B, a B, a D, an E, an A, C, A, E. That's my third quiz. Let's mark it. Nope. Nope. Yep. Nope. 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 Ugh. 2 out of 10 on this one. Not doing well at all. Okay, let's cover them up. Sorry, I'll get another one so I don't have the opportunity to kind of cheat a little bit. A, B, C, D, E. A, B, C, D, E. Just to be kind of funny. Okay, let's mark it. No, got the second one, got the third one. Oh, no, sorry. Didn't get the first one, didn't get the second one, didn't get the third one, didn't get the fourth one, didn't get the fifth one. I did get that one. I did get that one. No, no, and no. Another 3 out of 10. Okay, so now let's talk about why we're doing this. We're doing this to discover some new vocabulary. And what we're doing is we're looking at the probability of passing a quiz. And that's our experiment. That's what we were playing around with. Could I pass this quiz? And I didn't. I took 4 pretend quizzes and I didn't pass one. The simulation, new word, is the experiment that models taking each quiz. The experimental probability is the probability of the actual event occurring, me passing, and unfortunately I didn't. The event is the set of possible outcomes, and the trial is each repetition. So some new vocab is simulation, experimental probability, event, and trial. So the event in our case is passing. The trial is each row, each pretend quiz. And in our example, the experimental probability, and this is going to be another formula that we've got to have memorized, is the number of desired outcomes. So that would be correct answers over the total number of trials. So 3 out of 10, 2 out of 10, 2 out of 10, 3 out of 10. Okay, so what did we get here on the first page? We got some beautiful terminology. Simulation is running an experiment. An event is actually what we're looking to do, pass the quiz. A trial is each repetition of running the quiz, okay, running the event that we're looking at. And experimental probability is looking at the desired outcomes, what we're looking to do, over the number of total trials. Okay, when we're ready, let's flip our page. Now, let's take a look at what we're seeing here at the top of the page. And that capital P out in front of the brackets refers to the word probability. So this is asking probability of passing a quiz. Now, a couple kind of quick things for your own understanding. Every time you see the word possibility, or probability rather, my recommendation would be to set up a beautiful blank fraction for yourself. Because the word probability, the word fraction, the word decimal, the word percent, the word rational, they all roughly mean the same thing, okay? Bottom number represents the total, what things are out of. Top number represents the desired. This is kind of our everyday language. So, probability of passing a quiz. Well, I took 4 pretend quizzes and I didn't pass any of them. Not one. So, total number of quizzes, did I attain what I was desiring? No. Probability of getting over 30% on a quiz. Why don't we change that just slightly and getting 30% or greater? Now, why did I change it? 4 quizzes in total. Out of my 4 quizzes, I had 2 of them that I got 30%. I didn't get any that I got greater than that, but that leaves me with a probability of 2 out of 4, or 1/2. Probability of getting a correct answer. Now, let's think about that. I took 4 quizzes, and there were 10 questions in each quiz. So that actually means that I wrote down 40 answers. And out of those 40 answers, I had a 3 on one quiz, a 3 on another quiz, a 2 on another quiz, and a 2 on another quiz. So I actually had 10 out of 40, or 1/4, or 25% of my questions correct. Remember, probability looks at desired over total. Desired over total. And every probability question is going to be a fraction. Okay, let's look at another example. The following results were obtained when a die was tossed 100 times. Kind of an important piece of information, because I'm pretending that I'm taking this die and I'm rolling it 100 times. 21 out of the 100 times, a 1 popped up. 11 out of the 100 times, a 2 was rolled. 8 out of the 100 times, a 3 was rolled. 24 out of 100 times, a 4 was rolled. 10 out of 100 times, a 5 was rolled. And 26 out of 100 times, a 6 was rolled. So die result is the roll. Frequency, 21 and 11 and 8 and 24 and 10 and 26. That adds up to my 100 rolls. What is the experimental probability of rolling a 5? So I'm writing down what I'm looking for, probability of rolling a 5, and I'm going to write down a blank fraction. I always attack the bottom number first. So the bottom number is the total number of rolls. Out of those total number of rolls, how many of them were a 5? 1 out of 10 probability, 10% probability. What is the probability of rolling a 6? Again, write down what you're looking for, blank fraction. Bottom number is 100. It's always attacked first. And out of the 100, how many were a 6? 26. As a reduced fraction, 13 out of 50. That could be also 26%. Okay? What is the probability of rolling an even number? Again, write down what you're looking for. Fill in the bottom first. And then out of the rolls, how many are even numbers? Well, 2's considered an even number, 4's considered an even number, and 6 is considered an even number. 61 out of 100, or 61% of the time in this particular little experiment, I ended up with an even number. Okay, let's crank it up a little bit. What is the probability of not rolling an even number? Now, we're familiar with the word not from the permutation unit. And the permutation unit, every time we heard the word not, your brain was trained to think about reverse psych. And that's not going to change. Okay, so hold on. Let's take a look at this. We have two possible ways of attacking this: direct method or indirect method. Now, direct method says probability of not is 6. Bottom number is 100. And probability of not is 6, well, 21 occasions I had a 1. 11 occasions I had a 2. 8 occasions I had a 3. 24 occasions I had a 4. And 10 occasions I had a 5. So that probability of not a 6 is 74 out of 100. Which is 37 out of 50. Okay. Now, what about if I looked at it using indirect? Now, my layman's terms for indirect is what I like to call my reverse psych. So if you remember reverse psych said no restrictions minus opposite to the question. Well, in a probability type of scenario, because everything is in percentages, decimals, probabilities, rationals, no restrictions is always 1 or 100 out of 100. Okay, it's always 1. So we'll highlight that. Minus opposite to the question. Well, opposite to the question in this case would be rolling a 6. And we know rolling a 6 was 26 over 100. So if I take a look at this, 100 over 100 minus 26 over 100, that's going to give me the beautiful 74 over 100, or 37 out of 50. Direct technique, indirect technique, aka reverse psych, both producing the exact same answer. Now, the indirect technique can also be called a complementary event. It can also be called a complementary event. So hold on, let's put just a couple words and then we'll do another example. Complementary event is indirect and also called reverse psych. Now, what is the notation of the complementary event, that whole not notation? Do you see when you look at this particular symbol, it says probability of A, and then there's like a little apostrophe there? That little apostrophe is known as, we call it in math, A prime. And A prime is a simple way of looking at like the naught. So let me do another example for you. If I said to you, could you please calculate for me the probability of not being even? I could also write that as probability of E prime. Okay, the prime being the naught. And if I wanted to attack it using reverse psych, it would be 1. That stands for the no restrictions. Minus the probability of being even. So probability of E prime or not, no restrictions, minus the probability of being even. So let's take a look at it. We know that probability of even, I think we did that way back up here in example C, was 61 out of 100. Remember, 11 and 24 is 35, and 26 is 61. So the probability of not being even is that complementary event. Notice they complement, even and not even. They complementary event, and it's going to be 39 out of 100. So complementary event, indirect, and AKA reverse psych are all the same things. Okay, let's make sure you got everything off of this page, and then we'll flip. Okay, couple more examples. Let's keep looking. We're now going to look at a situation where a family would like to have 3 kids. A simulation was performed, so this is, an experiment. A simulation was performed to represent the real life situation. Coins were used to represent the sex of a child. Head meant girls, tails meant boys. 3 coins were tossed simultaneously 50 times. So hold on, let's take a look at the chart. 10 of the 50 times ended up with 0 girls and 3 boys. 15 of the 50 times was 1 girl and 2 boys. 16 of the 50 times, 2 girls and 1 boy. 9 of the 50 times, 3 girls and 0 boys. Remember, this isn't a simulation. This isn't real life. This is just a little game people were playing with coins. Determine the likelihood. This is just another way of wording probability. Some of your homework, you're going to see the words determine the likelihood. It just means what's the probability of an all-boy family. So I write down what I'm looking for, and I write down a beautiful blank fraction. I always attack the 50 or the bottom number, which is 50, and then I look for what I was desiring. I'm desiring an all-boy family. All-boy family. 10 out of 50, 1 out of 5. Okay, what is the likelihood, aka probability, of an all-girl family? Write down what I'm looking for. Beautiful blank fraction. Tack the bottom number. 50 trials, 10 plus 15 plus 16 plus 9, 50 trials. And how many are an all-girl family? 9 out of 50. So everything that we've just answered here in the last couple questions, they are all probability answers. A probability is a fraction, okay, in which the bottom number represents the total and the top number represents what we're looking for, the desired. Now, I just want to take a moment before we go on here for a second. I said to you earlier in the note that a fraction, a decimal, a percent, a probability, a rational, they're all the same thing. So when you give me your answers, you've got a couple choices. You can leave them in reduced fraction form, which is totally acceptable. If you're a decimal person, you could leave your answer as a decimal. And if you're a percent person, you could put your answer in percent. Oops. Now, I'm not saying that you have to give me every answer in all three forms. I'm not saying that at all. What I am saying is some of you will prefer to leave everything in fraction. I will accept it as long as it's reduced. I won't accept 10 over 50. I'll take off a half a mark. I will accept 1 over 5. I will accept decimal answers, and I will accept percent. If you choose to go to the percent route, make sure you put your percentage sign. Okay, now let's keep going, because what we've looked at so far is experimental probabilities, writing pretend quizzes, rolling or flipping coins to sort of simulate 3 coins to sort of simulate as if you were having 3 babies. Okay, now I want to move on and talk a little bit about the difference between theoretical probability and experimental probability. So hold on, let's keep going. Probability is used to predict the likelihood that a particular event is going to occur. So we use probability to help us make predictions on, whether things are going to occur. Experimental probability, so all of our experiments, gives us an estimate. So when I look at this boy-girl example, this might not be the way it happens in real life at all. This just happened to be one little experiment where I threw 3 coins 50 times and tallied the result. This could be completely bogus in the real world. It was an experiment. It's an estimate because the results will differ every time the experiment is conducted. So I could conduct this experiment of 50 throws of the coins today. I could run the same experiment tomorrow and get completely different results. I could run the experiment 3 weeks from now and get another completely different result. It's an experiment. Okay. Our goal is to eventually make predictions without having to actually perform the event. We want to make predictions. Well, how the heck do you do that? Well, theoretical probability is the actual likelihood that an event will occur. Notice the difference in the words. It's the actual versus the estimate. Again, how the heck do we do that? Well, given enough trials, the theoretical probability and the experimental will eventually equal each other out. And this is the case, you see this case in medicine a lot. When they have an experimental drug and they try it on people, okay? People sign up to be on a study, they're desperate, whether it's a cancer drug, whether it's even the vaccine, for the situation that we're going through right now. They put themselves forward and, a number of people are going through experimental process with the drug. And eventually, if a number of experiments are done, significant, like I'm not talking a couple hundred, I'm talking significant numbers of experiments, the results from those significant number of experiments will actually blend and mesh with what will actually happen in the real world. So when I look at the theoretical probability formula, it's actually no different than the experimental. Desired over total. Okay, desired over total. Now, let's talk about this, because it seems, well, if the formula is the same as Martel, like, you know, how are they different? Well, if you think back to question 1C, and 1C was the probability of rolling an even number, according to our experiment, there were 100 trials, and 61 of them were even numbers, 2 4s and 6s. That was our experiment. So you had a 61% chance, according to that experiment, of rolling an even number. Now, let's think of theoretical probability. If I put a dice in my hand right now, and I said to you, I want you to roll this die, what do you think the probability of getting an even number is? Well, bottom number represents how many sides are on that die, and the top number represents the desired, which is the even. How many of those 6 digits are even? 2, 4, and 6. So right now, look at the difference for something very, very simple that we can all visualize and understand. Experimental probability, that particular day that the experiment was run, they got a 61% chance of getting an even number. Theoretical probability is a 50% chance. So how would I eventually get these numbers closer? Significantly closer? I'd run the experiment day after day after day after day after day after day after day, and then I would tally up all those results, just like they do in medicine and just like they do in science. They don't just do a couple experiments and then put out a product, a drug for mass production. They do hundreds of thousands, millions of experiments looking for these two numbers to come together. Experimental probability, the result of a simulation. Theoretical probability, what we actually think is going to happen. Okay, really cool. Same formula. All right, let's keep looking at some more. Let's do some theoretical probability, just simple examples, just to get ourselves used to things. Probability of rolling a 4. Again, I can basically do this for every single question, guys, because I know they're all probabilities. Probability of rolling a 4, start with the bottom number. There's 6 sides. How many of those 6 sides are 4? Probability of rolling an even number. There's 6 sides. How many of them are even? Probability of flipping a head. 2 sides on the coin. One of them is a head. Probability of picking a queen. So imagine that I took a deck of cards and I fanned them out in front of you. Just beautiful fan of cards. And you were going to pick one for me. How many of those 52 cards are queens? Queen of hearts, queen of diamonds, queen of spades, queen of clubs. Probability of picking a face card. Again, I fan out the deck of cards. How many are face cards? 12 of them are. Jack, queen, king, hearts. Ew, sorry, that's a bad diamond. Diamonds, clubs, and spades. picking a red card, fan out the deck of cards. How many of the 52 cards are red? Half the deck. Probability of not picking a face card. Probability of not picking a face card. So let's look at it two different ways. Let's look at it direct, and let's look at it indirect. So probability of not a face means that there's 52 cards in the deck, but I'm removing these 12 cards from the deck. I'm removing all the jacks, so there goes 4. I'm removing all the queens, there goes another 4. And I'm removing all of the kings, there goes another 4. That means that 40 of the cards, that would be the aces, the 2s, the 3s, the 4s, the 5s, the 6s, the 7s, the 8s, the 9s, and the 10s, 40 of them would be not face cards. Okay, let's look at it indirect. No restrictions minus opposite to the question. So no restrictions in a probability is always 1. Opposite to the question would be the number of face cards. And I think we answered this earlier. That's 12 over 52. So 52 over 52 minus 12 over 52, 40 over 52. 10 over 13. Every single one of these examples that we just did are all theoretical. We didn't do one experiment. I didn't experiment with you at all. We just went on logic of theory. Okay? Logic and theory. Okay. One last little thing that I want to point out. It's kind of funny, but I want to point it out before we go. It says, remember, in experimental probability, we actually conduct an experiment to see what's going to happen. So let's look at a little example. Pretend that in a race with 4 other people, what is the probability that Mrs. Martell is going to win? So here's the situation. I get out on the track and I've got 4 other people with me. So it's me and 4 others. You can envision it, and we're going to run a race. Okay. The theoretical probability of Martell winning is a 1 out of 5 chance. Total number of participants, desired outcome is me winning, 20% chance. The experimental probability, and I mean, you guys know what I'm like as an athlete, you know the experimental probability of Martell winning is pretty well at 0%. So what you have to understand very clearly is the difference between experimental, running an experiment, versus theoretical. Okay? The formula doesn't change. It's still total on the bottom, desired on the top. Both formulas are still the same. They're just calculated completely differently. A theoretical probability involves no experiment. You just give me what you think's actually going to happen. Experimental probability are based on an experiment. Okay, I hope this helps. Take care of yourselves.